Okay. My internet shut out last time, as you knew, when I was making my asynchronous lecture. So if it for some reason goes, I don't know why it would again. Who knows? It's totally random, but I'm sure it will come right back. So just hang out. Um, okay. I am going to talk tonight about finishing 9.5. There wasn't a whole lot to do, like I said, just because there aren't a lot of exercises for you guys to practice this on, so I don't want to spend a whole ton of time on it. Most of what I want to talk about tonight is area from 9.6. So that's going to be my main focus. Now, 9.6 is really just going to be taking up the bulk of what you're doing from tonight through next week when you have your exam. It's not necessarily about the quantity in 9.6. It's not that it's necessarily a long section. It's just that you're going to need the time to let it kind of sink in and simmer and practice. So my goal is not to just inundate you with topic after topic here. I know it seems like, okay, well, we have today, and technically you have an asynchronous lecture scheduled for Monday. Depending on how far we get tonight, we might not even have very much to do Monday. I'm going to see where we leave off tonight. We might have like an example or two left over that I might have to cover asynchronously, which I'll do quickly because I'll be in this mindset. I might even just sit here and do it after class and then just release it so that you have it. But it's not going to be like a full 2-hour asynchronous lecture Monday because I don't have another 2 hours worth of content. And I mean, even if I wanted to go back and cover some of those Taylor series that we skipped over in the last chapter, I don't want to because like I said, I want you to kind of have some time to let all this simmer. I don't want to just inundate you with more information. So that's kind of my goal, is just to give you some time to process what you're doing with these polar coordinates. I know we had Thanksgiving break and I didn't see you last week. So I want to make sure that you guys have a chance to ask any questions that you've had and then talk about area. And then whatever I don't finish tonight, I'll release to you asynchronously. If there's not a lot, then there's not a lot. And you just need to focus on getting the 9.6 done. And the few examples I'll have left over from 9.5 that you'll have a couple of homework questions for. Before I get into finishing up 9.5, do you guys have anything you want to go over? I know some people were in the office hour asking some 9.4 questions. Any clarification that you guys feel would be helpful to you heading into 9.6 or 9.3?
So integral tables, can we and should we bring them for the test?
No. Can you? I mean, technically, I guess if you wanted to check your work using them, you could, but I don't want you using any formulas. The one thing that you're going to need for integration in 9.6 is really just that.
Yeah, there's one that they use.
Yeah, there's a rule that we used in trig integration. It's the double angle power reducing formula. So we're going to use that a lot in 9.6. But other than that, you will not need any crazy
formulas. Well, there's one that I used a lot that was the integral of the square root of x squared plus or minus a squared, and it gets this long thing for
I don't think it's going to pop up in this chapter. In 9.3 you use that?
Yeah, it's for all the integrating with the it seemed to come up a lot. I used it multiple times during my homework.
I see. That's a really good question, Greg, because technically in this section, I'm not really testing you on your ability to integrate. How about this? On your test, I'm not going to put up any sort of integral that would require you to use a table. Curious now. Was it on ArcLink? And you used it more than once, huh?
Yeah. Well, when I reduced it down to the square root of 1 plus u squared, I can then apply it to that to get, you know, the x over 2 square root of the thing, and yeah.
Interesting. I won't put anything on your test where it's not something that you'll be able to easily integrate using like some sort of basic u substitution, or maybe even parts, but I don't think you would be using any parts there. But I'm not
Right.
going to require anything that would use like a trig substitution, which sounds like what that formula would be needed for. Does that clarify?
Yeah.
And then I'll see, I haven't written your test yet, but when I get to the end, it should be very clear what sort of integration skill you should need. And then I will further clarify. If there's a problem that for some reason I'm really in love with and I want to leave it on your test and I think the integration might be tricky, then I might revise that, but I'll let you know. But I doubt that would happen. Get that attached to test problems. Any other questions so far in the chapter? Okay. One thing I was just thinking about was, so you have your test a week from tonight for chapter 9, and a week from that date, so 2 weeks from tonight, is your final exam. I told you it would be here before you know it. It's December 15th. So when I see you next time, you're going to take your test on chapter 9. The time after that, you're going to take your final. Traditionally, I would see you twice a week, and on Monday, we would review for the final exam. I can't really do that with you because we're asynchronous. So what I'm going to do is, I think, let me look for it real quick. I might, no promises. Let me look if I have it before I even say so. I might have even like some sort of review sheet. If I don't, I'm just going to have to make myself available for questions. Let me see if I have one that I posted previously. I can never remember what I have and don't have. I know I have one for Calc 1. Do I have one for Calc 2? I don't know. Keys, our notes. I'm gonna have to look through, but so it's not that we're just gonna like not have anything that Monday of the final. What I'm probably gonna do is just carve out some time that's optional where we can meet to review. It'll probably be like right around the same time that I would normally see you, and I'm gonna record it. So if people come with questions, it'll be recorded. You can watch it, and I'll post the notes from the office hour like I always do. But I don't know how else to do it because we're asynchronous. But I want to make sure you have that review time because you'll have that week in between your Chapter 9 test and your final exam. So that'll all be time that is set up for you to review. I don't see one. It's possible that I have one somewhere. I'll have to look.
I have a question on the Chapter 9 test. How quickly are you going to turn it around so we know what grade we got so we can prepare for what grade we need for the final?
It'll be quick because for that reason specifically, but also just because I mean, we're down to like 10 of you at this point, maybe 11. And it doesn't take me as long to grade them now as it used to. Also, is this my class? Maybe. Sorry, I'm looking for this review sheet still. So it doesn't take me as long to grade them. And I also just, it's like one more thing off my to-do list. So since I can get them done quickly, I will turn them around quickly. So
Cool.
Yeah, definitely by Monday. So but probably even before that. Yeah. Anything else before I start talking about 9.5? I haven't seen you guys in a while, so I want to make sure. We're down to 7 of you tonight. Wow. All right. Okay, then let's finish this out. This is my last live online lecture, which is kind of exciting, I guess. Unless COVID goes berserk and my spring class is moved online. One never knows what will happen. All right, last time we were talking about graphing parametric, no. Oh yeah, we were graphing polar equations and we were finding corresponding parametric equations for those graphs. So we really spent a lot of time building up a table of values using thetas that increase from 0 to 2 pi, and then talking about the corresponding R values and how to use those values to graph the function, or graph the polar graph. I should stop calling it a function. It's just kind of the way that I have gotten so used to saying things. But we're going to continue our discussion of 9.5 just with a couple more topics. I want to focus on, for a minute, finding intersection points, because we're going to have to do that in 9.6 whenever we're talking about finding areas between polar equations. We're going to need to know where the between is. So we're going to need to be able to find the intersection points of two polar graphs in order to figure out where our boundaries are. So I did want to talk about that. So this will be example 2. We're going to graph these in our calculator just because we've already done graphing by hand, and I don't really feel like we need to focus on that right now today. But we're going to graph these in our calculator, and then we're going to find intersection points. And the intersection points we're also going to find by hand. I don't know if your calculator will do this. It might. I have not actually, I don't think it will, but it's possible that it will. But it doesn't matter because I want exact values for intersection points. And a lot of times your graphs are going to intersect at specific multiples of pi, like it could be pi over 3 or 2 pi over 3 or something like that. And if you were to do this in your calculator, it would give you a decimal approximation anyway, which you might not think is a big deal, but it will be when you start to integrate and you have to use that value as a boundary. You don't want to have to do that. So we're going to find exact intersection points. So one set of equations I wanted to look at was R equals 1 plus the cosine of theta, and R equals 3 cosine theta. I might even have an example using these in 9.6. They sound really familiar, but they all start to sound familiar after a while. They all look basically like this. All right, so I'm going to graph these in my graphing calculator. Remember, you should be in polar mode if you're not already. Hit the mode button and make sure that you scroll down to polar and that you select that so that you end up, instead of in y equals, that you end up in r equals. And I'm going to make both of these have this magnifying glass thing. I always call it that. I know that's not actually what it is, but I like that little guy. Makes everything so much easier to see. So the first equation is going to be 1 plus the cosine of theta.
Quick question. How did you do the magnifying glass again? Because I forgot. I was
that's
writing
fine.
instead of looking.
No problem. You hover over it with your cursor. Just pick whichever one you want and then hit enter. And then I don't know if you have a CE or not. I think you do have a CE.
I got it.
CE, okay, yeah, it'll ask you first what colors. You can always change that. And then scroll down to line and then left or right arrow to sift through and see which options are available. I think it's the second one. Yeah.
Thank you.
And then, okay. All right, so 1 plus cosine theta, and the other one is 3 cosine theta. 3 cosine theta. And then we'll graph them just so that we have the graph up there. We're, like I said, we're going to find the intersection points manually, but I just want to make sure that we have the graph there to look at. Now, this is going to look a little bit weird to you for a couple of reasons. One, they look more like ovals when they're not supposed to be. And you're going to want to zoom in to see the features. So go to zoom, and I usually just hit zoom 2. And then you can decide where you want the center to be. Since you can see the pictures a little bit further off to the right, if you want the center to be more like in the center of your picture, you can scroll over there. You can hover your cursor over wherever you want it to go. And then you can hit enter. And then that's where it's going to center the zoom. Now, mine probably looks a little different because my boundaries for my window might be a little different. So if I go to my window, note that my max right now is set to pi, not 2 pi. Now, that was fine for when I was graphing the circle 3 cosine theta. I know it doesn't look like a circle, it looks like an oval. But that was not okay when I was graphing this cardioid because it only graphed half. So most of the time, you should get a picture that looks like some sort of polar equation. It's usually these things make a full, maybe not a full circle, but they usually make the full way around. So if they don't, go to your window and check to see that your theta is high enough. I'm switching mine over to 2 pi. I know I need 2 pi in order to graph the cardioid. You guys, I can't even see where pi is at this angle. There we go. 2 pi. And then I'm going to graph again. There's the full one. Okay. And then notice that once it went to 2 pi, you can see that it graphed the circle twice because the circle only requires pi to get graphed, where the cardioid requires 2 pi. Okay, so this is what you're looking at. So when we're finding intersection points, we're going to be looking for some values here that are going to pop out of our equations. We're looking at an intersection point here, and we're looking at an intersection point down here. Now, what you'll often find, not often, but sometimes you'll end up with an additional intersection point that doesn't pop out. So you might need to check your graph to verify that, because something like 0, 0 doesn't always come out in your equations. So usually it's a good idea to check your graph just to verify. But I'm going to go ahead and show you these by hand, and then we can look back at our graphing calculators and sort of make that connection between what we found by hand and what our graphing calculator shows us. So we're really sort of using both of these options that we have available. So if I'm finding the intersection just like we would have done back in algebra when you were trying to find the intersection between 2 lines, if you just had y equals, you know, whatever function and then y equals another function, you would set them equal to each other. And you're going to do the same thing here, because if you're trying to find the intersection points, you want to know when their radius values are the same. Notice that no matter what happens here with this graph, at some point it scrolls its way around, and here is where the intersection point is, and the radius value on both graphs has to be the exact same at the intersection point. So you're going to set these two equal to each other, and you're going to solve for your values of theta. And note that I said values of theta because, as you know, these values are not unique. As you work your way around the circle, you're going to have usually more than one place where these graphs will intersect, and you can already see that you're going to have at least 2. So if you're trying to solve this one, you can subtract cosine from both sides, and you'll get 1 equals 2 cosine theta, and then cosine theta is equal to 1/2. And then you're thinking about the possible angles theta where this would be occurring. Now, cosine is positive in quadrant 1 and 4. Now, when you're looking for the quadrant 4 value, as you found out probably as you're doing your achieve homework, they're going to specify that they want this to be between 0 and 2 pi. It's a very standard instruction. So don't give one that's less than 0 or more than 2 pi. So I know, for instance, that the cosine of pi over 3 is 1/2. And we're going to also look at this on the graph just to make sure that's the case. But in quadrant 4, if you're looking for a reference angle, you're trying to figure out the angle in quadrant 4 that has theta equals, I should say a reference theta, pi over 3. That's going to be 2 pi minus pi over 3. if you don't remember all your angles from trig. So that'll be 5 pi over 3. And like I said, sometimes that value at the pole is not going to show up. And that's why it's really important to verify that on your graph, just due to the your theta angles for your equations. But notice that your first intersection value for pi over 3 is this radial line that goes up through here and hits at that intersection point. And then the one in quadrant 4 is 5 pi over 3. So same angle as a reference angle, but now in quadrant 4. So like, let's say that you screwed up and you forgot that cosine is positive in quadrant 4, and maybe you were thinking it was positive in quadrant 2. Well, if you got something like 2 pi over 3, you'd be looking over here, and then you'd be like, whoa, 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 wait a second, that can't be right. So it's really important that we use our graph in conjunction with the algebra and trig that we're doing here to solve these angles. I looked at Achieve, by the way, and it, from what I could tell, even though on your graph you can tell that these two are intersecting at 0, 0, I actually thought to look in advance, and Achieve was not looking for this value, from what I could tell. So if it doesn't come out in your work, I don't think you need to worry about it. But if for some reason you're putting your work down and it's saying that you didn't find all the angles, you could, or I'm sorry, all the points, you could always try 0, 0. But it did not look to me like they were looking for that. Oh, and by the way, you will be asked for the actual points. So you'll need to find the radius values are for which these points, for which these graphs intersect. So these are your theta values, and you're looking for these as points r theta. So we can say that when theta is pi over 3, and remember the radius has to be the same in both instances. That's the whole point. So you pick whichever equation you want to do. It's kind of like when you were doing your systems of equations in algebra, and you found one value, and then you used one equation or the other to solve the missing value. You pick. So I'm just going to go with this one. Why not? And then solve for r. So the cosine of pi over 3 we already know is a half. So r would be 3 halves. And you can do the same thing for 5 pi over 3. Use either equation you want. But the cosine of 5 pi over 3 is also going to be positive 1/2. Oh, why did I write 3 pi over 2? Sorry, it's 3 halves. I'm like in the pi zone here. Not like Thanksgiving pie. I had like a meltdown on Thanksgiving because my husband asked me to put the kids to bed so that he could enjoy his dessert. And when I came back, everyone was eating all the dessert. And I'm just like.
Now, when you said we could use any equation, but if we pick one, should we just use it for the second one too?
No, it doesn't matter.
It doesn't matter.
You'll get
Okay.
the same value either way. So if you pick either one, well, in both cases. We could have used r equals 1 plus cos theta both times. Or you could interchange them, doesn't matter. Okay, so when we were writing our points of intersection, you're writing your points out as r theta. So you have 3 halves, pi over 3, and 3 halves, 5 pi over 3. And it's a little bit harder to see the r value from here, I guess. I mean, technically you can eyeball it and it should make sense. But you can see your units are marked out here. This first tick mark is 1. That you can see on the x-axis, and on the y-axis you can see that tick mark is 1. So your radius, I know it is a little harder to see because you're thinking about this in terms of more like a hypotenuse, but this distance is where that 3 halves is. So that's your 1.5. So you should be able to eyeball it and it should make sense. I mean, if you got like a radius of 5 here, you'd be like, oh, radius of 5, that'd be way beyond our intersection. So just something to think about, just sort of to do like a mental check as you work your way through. We'll do one more of these, but does anyone have a question on this one? So for B, we'll do one more set of equations. This one is 1 plus sine theta and 1 plus cosine theta. And you can go ahead and start to enter this into your graphing calculator. I'm going to go back to Zoom Standard, by the way. Okay, so we have 1 plus sine theta, 1 plus cosine theta. I'm going to go with Zoom Standard for right now. And my window was already set from 0 to 2 pi, so I'm going to leave it there. All right, so there's one cardioid and there's another one. I'm going to zoom in from the center. So I'm just going to hit Zoom, 2, enter. And that's what your graph looks like. So you're trying to find the intersections. So what you're trying to solve for is going to be the angle at which your points intersect right here. And it looks like you might have to zoom in a little bit more. I'm going to zoom in again, 2, enter. If you can see what's happening down here, you also have an intersection. It's very, very hard to see unless you zoom in. But this will come out in your work that you'll be able to see that you have this other intersection point. So I'm going to zoom back out again so that you can see what I'm talking about. So we're looking for this point and then this point. It's not at the origin, it's in quadrant 3. So to find that intersection point, we're going to set these graphs equal to each other. When you subtract 1 on both sides, you're just going to get sine theta equals cosine theta. I did this one on purpose just because I feel like this equation, even though it's pretty straightforward, students have a hard time with it because they don't know what to do. They're like, what process am I supposed to use here to solve for theta? You can't really think about this one in terms of some sort of algebraic process, or you're really going to have to think about this more in terms of what it means when sine and cosine are equal to each other. So you're looking for theta such that the sine of theta and the cosine of theta have the exact same value. I know I basically just rewrote what you have there, but for some reason I feel like that makes it a little bit clearer. Maybe not. If you had Calc 1 with me, you probably saw this equation every now and then because I know it pops up when you're looking for critical numbers. I think it comes up in critical numbers. It comes somewhere. But what we're looking for is theta such that this is true. And if you think about values for which sine and cosine are the same, you should be thinking about pi over 4. Because you know that at pi over 4, the value of the sine and the value of the cosine are both going to be 1 over root 2, or if you rationalize, it was root 2 over 2. So this happened in quadrant 1 at pi over 4, but it can't happen in quadrant 2 or quadrant 4 because sine and cosine would have opposite signs there. But in quadrant 3, sine and cosine are both negative. So you know that you can use the same reference angle in quadrant 3, and the sine of 5 pi over 4 and the cosine of 5 pi over 4 will both be negative root 2 over 2. I'll do it that way. So these are your two angles theta, and if you think back to what your graph looked like, this should make sense because we had 1 point occurring in quadrant 1 and 1 point occurring in quadrant 3. Last time when we did one of these, we ended up having the same radius values for both points. You're not going to find that to be the case here. If you do, something is wrong. Look at the distance. I was hoping that would hold because it looks better when it's dimmer. The distance between the origin and your intersection point in quadrant 1 is much greater than the distance between the origin and your intersection point in quadrant 3. So this is a much smaller value for R. So that's something that you should be thinking about as you find your values for R, that this value should be greater in quadrant 1 than the value in quadrant 3. But we'll do that now. And like I said, you can use either equation to find that because R is going to be the same at these two angles. So I'll just use the first one. So we'll say 1 plus sine pi over 4, which is 1 plus root 2 over 2, and 1 plus sine 5 pi over 4. Well, remember that we said that in quadrant 3, sine was negative. So it's 1 minus root 2 over 2. And here's where you're seeing that difference between the values. 1 plus root 2 over 2 and 1 minus root 2 over 2. This value is definitely greater than that one. So if we're listing these as points, which we are going to be doing, you'll have 1 plus root 2 over 2, pi over 4, and 1 minus root 2 over 2, 5 pi over 4. So that's how you find intersection points. That's not going to get any harder than just solving those trig equations. It kind of just depends on the equation you have. Any questions on example 2? So for example 3, actually, I'm going to give you a formula first. Your book doesn't actually have this formula. I'm going to give you this formula, and you may use this formula on your test because I'm giving it to you to use. It drives me crazy a little bit that your book doesn't give you the formula, but I'm going to give it to you as a theorem. Slope and polar form. So we talked about how to find derivatives for parametric equations. Now we'll talk about how to find them for polar equations. You won't be doing very much of it, but you will have to do it from time to time. So to find the slope in polar form, if f is a differentiable function of theta, then the slope of the tangent line to the graph of r equals f of theta at the point r theta is dy dx equals dy d theta over dx d theta. This is f of theta times the cosine of theta plus f prime of theta times the sine of theta divided by negative f of theta sine theta plus f prime of theta cosine theta. Now this is provided dx d theta does not equal 0. get your point.
On the bottom, is that a negative f theta?
Yes.
Okay.
No, I don't see that they give you that. That's fine. Like I said, you may use the formula. That's totally fine. Okay, so we are going to find dy dx. Example 3. Find dy dx for r equals 7 minus 2 cosine theta. And we don't need to look at this for too many points. We'll just focus on this at theta equals pi over 3. Okay, now, just so that you're aware, the reason your book doesn't give you this formula is because they want you to parameterize your equations and just find dy dx by brute force, which is fine if for whatever reason you can't find your notes, you don't know what the formula is, you can always do that. I'm going to start you out on that, and then I'm going to use the formula. I just want you to be aware of another method so that if you're looking through on the answer at Achieve, at the solution process, that you're not completely like, wait, where did this come from? I don't get it. So their process is just to let x equal r cosine theta, y equals r sine theta, and then you have x equals, if r is 7 minus 2 cosine theta, then just letting x be that r and then cosine theta. And then again, r, but sine theta. So if you would like to use this method instead of using the formula, then you can find dx d theta, dy d theta, and then just take the quotient of dy d theta, dx d theta. That's fine. You're going to get the same answer that you would if you were using this formula. But like I said, I don't think you'll see this formula on Achieve. So I didn't want you to be totally confused about why this was done. Okay, questions before I go through this derivative? Wonderful. So dy dx is f of theta, which is r. So r is f of theta. So we're going to go with that first. 7 minus 2 cosine theta. Multiply that by cosine theta. You can see now where the formula comes from, just by using the derivatives here. Plus f prime of theta, so that would be r prime, which would just be 2 sine theta. The derivative of cosine is negative sine. And then you're multiplying that by sine theta. And then in the denominator, you have negative f of theta. So that's negative r times the sine of theta plus f prime of theta times the cosine of theta. Now, if I just ask you to find dy dx, then yeah, you should try to simplify this down a little bit. There's not a whole lot you can do, but if you're asked to find the derivative at a specific value of theta, which I have asked you to do, then you don't need to simplify this at all. You're just going to show that you're evaluating this for theta equals pi over 3. So if we have theta equals pi over 3, then you're just going to find the derivative value by letting theta be pi over 3 everywhere you see theta and just evaluating this expression. So it's just going to take a minute to simplify it down. It's not really anything hard, but it's just a little bit tedious in evaluating all of these trig functions at this value. And you know, as you can see here, even if you did it this method with turning these, parameterizing this polar equation, you would still end up with kind of crazy derivatives. So that's kind of what makes the formula a little bit nicer, because if you had to find dx d theta, you would have to use the chain rule here and make sure that you were using it correctly. And then for this one, you would have to either use the product rule, or you would have to turn this into sine 2 theta and use the chain rule. So it's definitely harder to do this method. I'm not trying to make anything super hard at this point. It's just making sure you've seen some things so that if you see them in the future, you know how to handle them. This is all just technically Calc 1 stuff. All right, so 7 minus twice. The cosine of pi over 3 is a half. And be careful with your parentheses. Cosine of pi over 3 is a half. The sine of pi over 3 is root 3 over 2. And then you'll just have to be careful with how you simplify this. Are there any questions here? I'm just going to do this in a couple of steps so that nothing gets lost. 2 times a half is 1. So 7 minus 1 is 6. If you want to do that in one step, that's fine. I don't know, it's kind of up to you how many steps you would like to use. I'm going to cancel out those 2's. Square root of 3 multiplied by itself is 3. And then I still have 1, 2 left over in the denominator. Minus 7 minus 1 is 6. Root 3 over 2 plus 2 of those will cancel out, and I'll just have root 3 over 2. 6 times a half is 3. And then here I can cancel out a 2 between the 2 and the 6. And I'll have minus 3 root 3 plus root 3 over 2. And then to simplify this complex fraction, just multiply every term by 2. And you'll get 6 plus 3 divided by negative 6 root 3 plus the square root of 3. And then you can simplify this one more time. As 9 divided by negative 6 root 3 plus 1 is negative 5 root 3. And you don't need to rationalize the denominator. That's fine. Leave it as is. That is how you find slope in polar form. Okay. Let's see. Okay, the last thing I was going to do in this section was talk about arc length. And again, there aren't a whole lot of problems for you to do here. There might be like 2 on your homework just because there wasn't a lot that was available. There's really not even much covered in your book for me to assign by hand, so I just left it as is. But I'm going to give you the theorem for arc length. This is arc length of the graph of a polar equation. If a curve C is represented by the polar equation r equals f of theta, theta is between alpha and beta. When we're talking about polar integration, we're always going to be using alpha and beta instead of a and b, just the way the notation is. Nothing super crazy there. And if f prime of theta equals dr d theta is continuous, on an interval containing alpha and beta, then the arc length, little s of C, from theta equals alpha to theta equals beta is the integral from alpha to beta. And this is going to look sort of similar to what you've seen before for arc length. We talked about it a couple of different times now in various contexts. We're going to take the square root and we're going to take r squared plus dr d theta quantity squared d theta. So I'm going to give you one example of how to find arc length for a polar equation. This will be example 4. The arc length for r equals the sine squared of theta over 2 on the interval from 0 to pi. So in our formula, we're going to be using r, but we're also going to be using dr d theta. So that's the first thing we're going to find. If you find that it's easier for you to take the derivative by rewriting this, I tend to think that that's easier, so I'm going to rewrite mine. So instead of writing it as sine squared theta over 2, I'm going to write it as sine theta over 2 quantity squared. I did this a lot in Calc 1 just because it's a lot easier to see that you have a composite function when you have these parentheses and you have an entire function being taken to the second power versus this notation where it's a little bit less obvious. So let's go ahead and use the chain rule to find drd theta. So we're going to bring the 2 out front, rewrite the inside function, decrease the power by 1, and then we're going to multiply by the derivative of the inside function. Now, the inside function's derivative is also going to use the chain rule. Remember that the derivative of sine u is cosine u du dx, or in our case, it's going to be du d theta. So we're going to be looking here at cosine theta over 2, and then the derivative of theta over 2 is a half. So here we just use the chain rule twice. I'm going to simplify this slightly. There's not a whole ton we can do to it. Before I do that, does anyone have a question about drd theta? So the 2 and 1/2 are going to cancel. Remember, you cannot mess with what's inside your trig function. This is part of the angle. You can't cancel it with anything. You can't multiply these together. The only way you're going to be able to simplify this is just saying sine theta over 2 times cosine theta over 2. And we're going to start to build this now into our formula for finding the arc length, which I have right up here. You have it right there on your paper. So this is going to be the integral from 0 to pi. We don't have a constant multiple of anything out front. A lot of times we do that for surface area. We don't have that for arc length. We're going to take r squared plus drd theta squared. So r squared, well, r is already being squared. If you want to look at this variation of it, you might find that a little bit easier to see. But r squared would be sine squared theta over 2 squared, which is the sine to the 4th power of theta over 2. And you might even want to write that in this form so it's a little bit more obvious what's happening. I'm going to do that with mine. So I'm going to write my square root. And we're going to write this as sine theta over 2 to the 4th power. So that's your r squared. And then I'm going to add this to drd theta quantity squared. So here's your drd theta. When we square that, if I were you, I'd square each one of these factors instead of showing that entire product being squared. So this will be sine theta over 2 squared, cosine theta over 2 squared d theta. Any questions on that? All right, so you've seen this type of process before. You're going to factor out whatever you can in order to simplify this down to something that looks more familiar to you. And before you even write anything, you might be thinking like, well, wouldn't this be nice if I had sine squared u plus cosine squared u? Well, you can actually get that if you factor out 2 of these factors of sine theta over 2. So I'm going to take out sine theta over 2 quantity squared. And what that's going to leave me with is I'll still have 2 factors of sine theta over 2. And I'll have cosine theta over 2 squared as well. Now, it does not matter what the angle is. All you need is the angle to be the same. So what if the angle is theta, theta over 2, 15 theta, it doesn't matter as long as the angle is the same in both of these functions. If it's the same angle, then when you square them and add them together, you're going to use a Pythagorean identity and get 1. So you're going to simplify this down now so that you have the square root of sine theta over 2 squared. The square root of this quantity squared is just sine theta over 2. This quantity right here simplifies down to 1. So your whole integral just simplifies down to sine theta over 2 theta. Questions here? Okay. And now you're going to integrate. You can do a u substitution if you want. If you don't feel like you need one, that's fine. If you do a u substitution, you're going to let u be theta over 2 or 1/2 theta if you find that easier to see. And then du d theta or du, you could say that is 1/2 d theta. You don't have 1/2 d theta, you just have d theta. So however you want to do that. If you want to change your limits of integration, now you're getting a little bit crazy. You might just want to hold off for a minute, or you can even just label them as being theta equals pi, theta equals 0, and then you have 1/2 sine of u d over 2, not 1/2. Yikes. So used to doing 1/2. du is your d theta, then you have sine u. And the derivative of cosine u is negative sine u, so the derivative of negative cosine u is sine u. And then you can sub your u back in. And evaluate. So you'll have negative 2 cosine pi over 2 plus twice the cosine of 0. This quantity is 0, and the cosine of 0 is 1. Therefore, your arc length is 2. So you'll see some of those, a couple of those, maybe like 2 in your homework. Like I said, there's not much to do. The reason being, there's not a whole lot here that you can do by hand using the integration techniques that you have. Some of them are in there and they require a computer algebra system. Okay, that's all I have to say about 9.5. I'm going to start talking about area in 9.6. Before I do that, are there any questions on 9.5? Oh my gosh, you guys are wearing 2 turtlenecks. You can't tell because they're both black. 2 turtlenecks. That's how cold I am. I used to work in this very cold office, and the people across from the aisle from me used to wear fingerless gloves.
I got a blanket on my lap, so I understand.
I was wearing a blanket in the office for the other day. I don't remember if you were in that one, Becky. Oh, I think you were in that one because I was like awkwardly holding up the blanket while I went to go get something.
Probably.
I know. See, that's one of the nice things about being at home, right? Like in class, most people don't have blankets with them, but I guess it's not that cold. You're just relying on ECC for heat in that case. They're usually pretty good about that. Okay. Do you guys remember those things called Snuggies? Does anyone remember the Snuggie?
They still have those.
Do they still have them? What
Oh,
was
yeah.
it? What was a Snuggie? Was it like a burrito blanket that you like got into?
Depends on what version, but basically,
It's kind of like a blanket with sleeves.
yeah.
That's right. That's right. I knew it was a thing, and the other day I was thinking about it. I was like, what was that Snuggie thing? You're right. All right. 9-6 area and polar coordinates. I didn't get cold for the longest time. I was pregnant for years, and like then all of a sudden, like I haven't been pregnant in like 2 years, and now I'm just freezing all the time. And I feel bad now that I probably just thought my kids were fine all those years. I'm like, they don't need coats. It's not that cold, but it was really just because I was overheating all the time. All right, I'm going to give you a theorem here, and it's going to be the only one you're going to see in this entire section, and it's very short. But your book knows how to take anything and make it really long. You know what? I'm just going to tell you it's area and polar coordinates. And I'm going to give you the formula because that's what you're going to be using. So this is going to be the integral from alpha to beta. And it's 1/2 r squared d theta. No matter how crazy of lead I buy, it still just breaks. So this is the formula we're going to be using when we're talking about finding area regions. I'm going to start out just by sort of building this. We're going to build this slowly. First, we're just going to find the area of a simple polar region. And then we'll talk about maybe finding the area of a region that has more parts to it, but maybe isolating one part or two. Then we're going to talk about finding areas in between different parts of figures. And what I was explaining in the office hour, because sorry, by the way, if I sort of built this 9-6 up as something so crazy, it's not that bad. Some of the questions can be confusing with the setup. The integration itself in this section, the problems are all basically just going to be reusing the power reducing formulas. So you're not going to see any super crazy integration here. It's going to be the setups, and only setups when you're being asked to isolate specific areas of intersecting curves. That's when it gets a little bit more tricky. But my first example, I'm just going to give you a basic polar equation, and we'll talk about how to find the area inside this polar curve. And we'll just sort of build this up. I have all my examples written on like different places, and I combined them here, but now I must find them. So the first one will be simple one. We're going to call this find the area we'll just say find the area enclosed by r equals 4 plus 4 sine theta. Now, if you would like, you can feel free to put this in your graphing calculator. I'm going to be doing that for these just because it's going to be really helpful for us to find our bounds or just sort of get an idea of where we're integrating to and from. I do think, though, that you've probably seen enough equations of this form to get a sense for what you're expecting. I mean, this is just another one that is like of the same form that we already had in here. But I'm going to go ahead and get rid of that. Okay, 4 plus 4 sine theta. Make sure you're going from 0 to 2 pi. If you want, actually, we might even want to play around with this. I'm kind of glad I said that. because it's going to be really, really important to us to know where this graph starts and where it completes its first cycle. You can graph portions of this just by switching out that theta max. So if I were to only graph this from 0 to pi over 2, I do think this is really instructive. If you don't want to do this, that's fine. You might want to just look at mine. If I were to graph this from only 0 to pi over 2, it's only going to graph, oh, I'm zoomed in. Sorry, I have to zoom back out again. Zoom 6. Pi over 2. It's only going to graph the region between 0 and pi over 2. And I think you kind of have to get used to thinking about the way that these graphs are done. And hopefully, if you really got a chance to get working on that polar equations assignment, you're getting a really good sense for how the radius and the angle interact with one another. But thinking about this, I know I showed it with like the pencil sweep, but I'm going from the angle 0 up to the angle pi over 2. Now, I cut mine off at pi over 2 just to sort of illustrate how much of this region we need to cover. I said that we're looking for the area that's enclosed by this graph. So I want to graph the whole thing. Well, if graphing from 0 to pi over 2 gave us this much, you can see now how changing that theta max is going to give us either more or less of the picture. So like, for instance, if I went from 0 to pi, well, now you're going to see that you have what looks like the top half of a figure graph. But you might say like, oh, maybe the area is enclosed here, and maybe we're just looking at the area above the x-axis. But that's not what I asked. So there might be specific instances where you might be asked to find, for instance, the area of the shaded region, and you might be only given the part of this graph that's above the x-axis. Well, if that was the case, then absolutely, oh, this is a terrible rendition, by the way, of what's actually being displayed on your screen. Then yeah, you would definitely be looking from 0 to pi in that case. But I did not ask you to look only above the x-axis. I asked you to graph the area that's enclosed. So we're going to go all the way up to 2 pi so that you can see this. And if you have your little magnifying glass, that helps you to see it better. And you can see that it's graphed one time, and it looks like that. The reason I feel like it's kind of instructive to show you that is, like I said, because sometimes you'll be asked to find the area of just the shaded region. So if the only region that was shaded was above the x-axis or below the x-axis, you'd have to determine what your bounds for theta would be. So if I was looking above the x-axis, I'd be going from 0 to pi. If I was going below the x-axis, I'd be looking at pi to 2 pi. Just kind of making your sweep around. So in order to enclose this, my angle theta is covering radius values all the way up through pi over 2. You can see how r increases. And then heading back down again to pi, you can see that r starts to decrease. And then the r value gets much smaller as we head towards 3 pi over 2. So you've got a really, really small radius here compared to what it was way up there. And by the time it gets really close to 3 pi over 2, it's heading towards 0, your value for r. And then as it moves away from 3 pi over 2, heading back to 2 pi again, r gets longer as it draws out this curve. So when we set up our integral, I like to put my 1/2 in front of the integral. I know that usually we do that just because it kind of gets in the way inside the integral. But it's our bounds that are the hard part. And in this case, they should not be that hard. I feel like we should be able to look at this and get a really good sense for, okay, this graph is being drawn from 0 all the way to pi over 2. Or I'm sorry, 2 pi, not pi over 2. I know it's not a circle, but it has this same behavior where it starts and ends at the same point. And really, you could start this graph wherever you wanted. Note that if I wanted to start the graph at pi over 2 and end it at pi over 2 plus 2 pi, I could do that also. It would just start being graphed in the same place. Let's say I wanted to draw this graph from negative pi over 2 to positive 3 pi over 2. I could do that also. So you have actually a lot of different options available to you when you're setting up your integration bounds. So if I wanted to go, for instance, from negative pi over 2 all the way up to 3 pi over 2, I could also graph this whole thing. Let's say I went from negative pi over 2 just to pi over 2, I would only get the right side of the graph. So that would give me the right side. If I went back here and made it go to 3 pi over 2, I should get the whole thing. So it's kind of up to you. I mean, technically, we could have an infinite number of different correct answers here as far as where you're going from alpha to beta, because you can graph this region in an infinite number of ways with different starting and ending points. I tend to pick the simplest ones, which for me go from 0 to 2 pi. But you could start at a different spot. You could start at pi if you wanted, and then you could go up to 3 pi. You could start at negative pi and go up to positive pi. It's up to you. Play around with it. Just because your bounds are different doesn't mean you did the wrong thing. I'm going to put the rest of this together, but I want to know if there are any questions on your upper and lower limits of integration.
Where did we get the 1/2 again from?
Oh, from your formula.
Oh, okay, thanks.
From your formula.
Spent a lot of time drawing, so I wasn't
No,
thinking.
no, it's fine. Actually, I'm really glad you asked that, because some of you might be wondering, like, well, technically this graph has symmetry. It's the same on the right and the left. If you wanted to use symmetry, you could technically set this up by only finding the area of like the right side or the left side, and then you could multiply it by 2, and then you wouldn't even have a 1/2 there, because 2 times 1/2 would give you 1. So some students like to use symmetry depending on what the limits of integration are. So if you wanted to use symmetry, I'm going to make a note here. You could use symmetry, and then you could take twice the area that's going from negative pi over 2 to pi over 2 of r squared d theta. So that's just one more way that you could set this up. You couldn't do twice the area from 0 to pi, because the area on the top and the bottom is not going to be the same. But you, like I said, you play around with this. I even think changing these values really helps to give you a sense of what will and what won't work, and it's very instructive in and of itself. But I'm going to focus on just taking the whole thing right now instead of using symmetry. So the 1/2 came from the formula. Inside our integrand, we're going to put r squared in there. Right now, I'm just going to write this as 4 plus 4 sine theta quantity squared d theta. Okay, so the hard part was just finding the upper and lower limits of integration. For a region like this, I don't even expect that to be a hard part for you. Questions on the setup? Other questions? Okay, so at this point, now you have essentially a Calc 1 problem, maybe technically a 7.2 Calc 2 problem, because I don't know if you use very many power reducing formulas in Calc 1, but same idea. It's review at this point. Don't forget to multiply this out by foiling it. This is not 16 plus 16 sine squared theta. You must FOIL it out. And I'm even going to write that whole stuff out just because I want to make sure we all do it. Not everybody will need to actually write this out. Some of you can FOIL in your head. That's fine. Just make sure that you're actually multiplying both binomials out completely. And now you can start to simplify the integrand. So you'll have 16, and And then plus 16 sine theta plus 16 sine theta gives you plus 32. Oh, yeah, 32 sine theta. Maybe I'm so, you know what? I'm always breaking. It doesn't matter how cold I am. The lead was going to break regardless. I have no excuses. Plus 16 sine squared theta d theta. Okay, these first two terms we can integrate just like we did in Calc 1. The last term we're going to need to use a power reducing formula for. If you don't remember what they are, I'm going to remind you right now because you're going to need both of them. Sine squared u is 1/2 times 1 minus sine 2u. The cosine one is the plus variation. So if you need to put a big box around these or highlight them or you have them on a separate cheat sheet of formulas that you use all the time, that's fine. You're going to use them all the time. Another issue that students have in this section is just keeping track of their work and integrating properly. I know it seems really obvious, but it's not supposed to be a really difficult integral, but it does require you to really focus on your signs, S-I-G-N-S, and just pay attention to the details. So I'm going to write everything out so mine is extremely clear before I start integrating. So I'm going to take my sine squared theta and I'm going to switch that into 1/2 times 1 minus the sine of 2 theta. And then I'm going to simplify again. And then I'm going to simplify again before I integrate. I don't want to lose anything. So we have 16 plus 32 sine theta. 16 times 1/2 is 8. So we'll have plus 8. 8 times 1 is still 8. And then minus 8 sine 2 theta. If you want to multiply the 1/2 in here just to decrease all these, that's fine. If you want to hold off, that's also fine. I'm going to hold off. Anything that doesn't seem super obvious to me, I'm going to wait on. 16 plus 8 is 24. So I'm going to have 24 plus 32 sine theta minus 8 sine 2 theta d theta. And because I don't want to deal with these larger coefficients, here's where I'm going to go ahead and just divide that 2 out. Or technically, you can think about this as just factoring out a 2 and multiplying it by 1/2. Or if you want to think about it as multiplying the 1/2 in, also fine. We'll have 12 plus 16 sine theta minus 4 sine 2 theta d theta. Okay, and now we're ready. Some of you maybe even started integrating here and you just carry these terms down. I know when I did that, people were just like, can you do this integration all at once? So I'm just going to do my integration all at once. All right, so the integral of 12 d theta is 12 theta. If we're trying to get sine, we originally needed to start out with a negative cosine. So we'll have negative 16 cosine theta. Don't forget that with sine 2 theta, technically you need a u substitution, but I did give you that formula that said if you had sine k theta, you would just divide by k. So you've probably gotten used to doing that at this point. So that is fine. So you'll have minus 4 divided by 2 cosine 2 theta, and we'll take that from 0 to 2 pi. Oh, sorry, this is positive, not negative, cosine theta. The derivative of cosine theta is negative sine.
You said the sine k theta over k or something?
Yeah,
That
it's the
would give us-
integral of sine k theta d theta is negative 1 over k cosine theta plus c. We had the same type of thing for the exponential functions, e to the kx. We can do the same thing for cosine. Cosine k theta. I couldn't make up my mind what I was going to do there. Oh,
Thank
k theta, sorry. Not just theta. Plus c. Yes, you can do that as well. Always, I mean, what I like to do, especially with trig functions, is make sure that my derivatives match up when I go the other direction, just so that nothing gets lost. So if I switch this 4 over 2 to a 2, then I'll be able to just take the derivative and make sure I get what I started with. So the derivative of 12 theta with respect to theta is 12. The derivative of cosine is negative sine. We've switched. So everything's okay there. And then for cosine, you get negative sine. And then when you use the chain rule, 2 times 2 gets you to that 4. Just verify. Any questions here? All right, so now we're just going to evaluate this from 0 to 2 pi. So you'll have 12 times 2 pi minus 16 times the cosine of 2 pi plus twice the cosine of 4 pi minus 0. Don't forget to do your minus a negative in this case. Cosine 0 minus 2 cosine 0. You'll have 24 pi. The cosine of 2 pi is the cosine of 0, which is 1. So you'll have minus 16. The cosine of 4 pi is also the cosine of 0. So you'll have plus 2, plus 16, and then minus 2. So those are all going to go, and you're just going to be left with 24 pi. All right, questions on example 1?
Nope.
Example 2 is going to employ some techniques we used in 9.4 when we were graphing polar equations. Specifically, the last example I did. We are going to find the area of one petal of r equals sine 3 theta for sine 3 theta. Trying to figure out, last time I think I did this with a cosine. I should know because I spent so much time writing it up for you. Yeah, I think it was a cosine. It doesn't really make a difference. They're basically the same. Okay. The only reason I wanted to switch up the function was because I wanted us to find r equals 0 using this function instead of the other one. Okay, go ahead and put this in your graphing calculator. I told you one petal, so it's a rose curve. If you don't recognize the form yet, that's okay. We have 4 sine 3 theta. Mine right now is zoomed. No, maybe I'm zoom regular, but I'm going to zoom standard just to see. Oh, and look at that. It graphs it twice. You can tell that because of the little loopy guy that I selected. The rose curves only need to go from 0 to pi. So it doesn't really matter. I mostly just want you to see the graph. But like I said, I think it's good to kind of see how this works. If you go from 0 to pi, you'll see that it only graphs it once, but you'll get the whole figure. Okay, so what we're going to do is we're going to figure out how to find the area of one petal. There are a couple of different ways of doing this. There are a couple of different ways of doing this. But what I'm going to focus on is what we did in the last example of the last lecture, the one where my internet cut out. And that's what we're going to be finding here is places where this particular petal, whichever one we choose, kind of starts and stops. So you'll see that when we graphed ours, mine isn't going to graph itself again. I believe, though, that it started. Yeah. So it kind of started right here. It did one of these deals, came back down, did one of these deals, and swung back around. Kind of like that, something like that. But it started right here, and it swung up this direction. So as theta increased, your value of r increased until you got to the petal tip, and then eventually you ended up at some value theta such that your radius was 0 again. So if you swing back around, you're trying to figure out to get from one part of the petal to the other. Technically, it doesn't matter, but the easiest way you're going to find that is by going from your starting point, where your radius is 0, the starting point of your petal, to the ending point of the petal. So back where this meets again, where the graph starts to cross itself. I'm going to focus on this petal. It doesn't necessarily matter which one you focus on. This is just going to be the easiest one to work with. And what we're going to do is we're going to use this technique that we used in that last example, where we're trying to figure out where the radius value is 0. So r is going to be equal to 0 when 4 sine 3 theta equals 0. And this is going to happen. Your sine function is going to be equal to 0 when 3 theta equals 0. So sine 3 theta equals 0 when 3 theta equals 0. Because remember, I just need sine of 0 to get to 0. That doesn't work the same with cosine. The cosine of 0 is 1. But if 3 theta is 0, then I have this holding. And then I'm going to look for the next place where that would happen. So I also am looking at the next one. I can't jump up to 2 pi. I have to look for the next place where the sine function would be equal to 0. And that's going to be at pi. Or, sorry, when 3 theta equals pi. Getting ahead of myself here. So yes, technically 2 pi is also a place where sine 3 theta equals 0, but it's not in sequence. And I need this to be in sequence because remember, I need to hit the origin at the starting point, and then I need the next place where it hits the origin. If I skip ahead to 2 pi, then I'm going to hit the place after that where it hits the origin, and I'm going to actually be getting 2 petals at that point instead of 1. And that's not what we're looking for. We just want the area of 1 petal. Now, that would be fine if you knew you got the area of 2 petals, then you could just divide it in 2 and you'd have your area. But most likely, if you did that, it was by accident and you thought you were only getting 1. All right, so if I want 3 theta to equal 0, then I know that theta would have to be equal to 0. Divide both sides by 3. And if I want 3 theta to equal pi, then theta is going to be equal to pi over 3. Now, it's not necessarily the most obvious thing, and especially the way that I graph this makes it look a little bit shallow, but we actually have just trapped our petal in between theta equals 0 and theta equals pi over 3. So even though it's not necessarily the most visually obvious thing, you should be able to obtain a value and see that graphically it does make sense that we've trapped this petal in between these 2 radial lines. But here's, this work is basically just saying, okay, my petal started at theta equals 0 and that stopped at pi over 3. Nice thing about this is you can use your graphing calculator to verify this. So if you go back to your graphing calculator, mine's zoomed in right now. I can go back to Zoom Standard, fine, because I want to make sure that's right. And then what I can do is I can verify that if I go from 0 to pi over 3, that I'm only going to get 1 petal. So we'll do that by looking at our window, going from 0 to pi over 3, and then just making sure that it only graphs 1 petal. Okay, so that looks good. I can even zoom in. It's a little bit harder to see. I zoomed in slightly too far, but you can see that that's exactly 1 petal. Now, if you accidentally took this, for instance, to 2 pi over 3, because you use 2 pi instead of pi, then you're going to see that you're actually going to get this graph, which gives you 2 petals. And of course, if you took this all the way up to pi, you'll get your whole graph. So another way that you could have seen this, and it's not going to work for every single situation, some of them are going to be more obvious than others, is if you note that this function or this graph graphs itself from 0 to pi, it makes a whole complete graph, then, well, you'll know that a third of the graph, which is 1 petal, will graph itself from 0 to pi over 3. That's sort of another way of seeing the same thing, as long as you recognize that. So we're going to set up our petal from 0 to pi over 3. That, like in the last situation, does not necessarily have to be the case for all of you. Some of you might start at pi over 3 and end at 2 pi over 3. If you start at pi over 3 and end at 2 pi over 3, you're going to get this petal. If you start at 2 pi over 3 and end at pi, you're going to get this petal. So it kind of depends on where you start with that. I'm going to put this together, and before we do the integral, I'm going to make sure to check to see if you guys have any questions on this setup. Terrific, terrific. Okay, I'm going to simplify this. I just am taking a product to a power, so I'm going to apply that power to each factor in the product. So this is going to be 16 times sine squared 3 theta d theta. Technically, we don't need these parentheses. If it's too much, take them away. And we can do this because we have a product to a power, not a sum or difference to a power. In the last example, we had to FOIL that out because we were adding 2 terms together. Okay, my guess is you're going to want to simplify this by bringing that 16 out of the integral so you can focus on your integrand by itself. So that's what I'm going to do. 16 divided by 2 is 8. And then we're going to use a power reducing formula to simplify this down so that we can integrate it. I'm going to remind you of the formula. I know I just wrote it on the last page. Sine squared u is 1/2 times 1 minus sine 2u. Now, in this case, u is 3 theta. So we're going to take 1/2 times 1 minus the sine of, well, if we're looking at 2u, then we're looking at twice 3 theta, which is 6 theta. Whatever you do, you cannot multiply this 1/2 into the 6. Be careful there. It's not going to be 1/2 minus sine 3 theta. Don't do that. If you weren't thinking of doing that, awesome. Then just ignore that comment. I've seen some crazy stuff over the years. All right, so I'm going to rewrite this as 1/2 times 1 minus the sine of 6 theta. I don't know. I've so many grouping symbols, guys. At some point, it is too many. We'll have to get rid of some of those. And I'm going to take this half and I'm going to multiply it outside with the 8 as 4. And that will leave me with 1 minus the sine of 6 theta d theta. Now we can integrate. So you can see here how so far, especially, all the integrals are looking similar. It's just that the setups that are going to be different depending on the type of polar equation you're given in the scenario. So let's go ahead and integrate. So we'll have theta. In order to get negative sine, we need to start out with positive cosine, and we'll divide by 6 because we are integrating. And then we'll evaluate that from 0 to pi over 3. Double check and make sure if you work your way backwards, you still get that derivative. If you want to multiply your 4 in, feel free. I'm just going to leave mine out. Before I proceed, are there any questions? So we have pi over 3 plus 1/6 times the cosine of 6 pi over 3. Well, 6 pi over 3 is 2 pi minus 0 minus 1/6 times the cosine of 0. Mm-hmm. 4 over 6 is simplifies to 2/3. The cosine of 2 pi is 1. And then minus, again, we have 2/3. And we'll get 4 pi over 3. Okay. Questions on example 2? Trying to show you guys a variety of graphs. So example 3 will be find the area of the inner loop of r equals 2 minus 4 cosine theta. And you'll want to go ahead and put this into your calculator. I don't remember where I left my bounds. I'm going to leave them just for now, just to see what happens. Zoom standard. That's what we're dealing with. You can kind of understand where this inner loop thing is coming from now. If you would like to sort of draw this so we can talk about it, I'll put it down on paper. By the way, it might be helpful to see where this started. So I might zoom it in a little bit. And our window is going from 0 to 2 pi, and it graphed one time. So maybe I'll just zoom this in a little bit. It might end up being too big for the screen, but I'm going to center it here in the center of the region. Yeah, it is a little too big. That's fine. Technically, we are just going to have to adjust the window here. Let's see. I don't know, maybe to 6. And graph. Okay. Did you all notice where this graph started? It's really helpful to see that. So it started here, and then it went down. Whoops. It started here at -2, and then it went down into the origin, and then it went kind of around like this, and then it went back down again. Did something like that. Not exactly, but something close to that. What we're focusing on is finding the area of the inner loop, which is this thing. That is the inner loop. This is where your graph started. You have some options here, and if I were you, I would use symmetry on something like this. On my drawing, it's not the most obvious thing that it's symmetric, but you should be able to see that on your graph. And a lot of times with these polar equations, you can take for granted that there is symmetry. You can see that the graph is going through this point at the origin. In case you were not sure, you could always zoom in a little bit more at the origin just to see what's happening. But you can see where this inner loop will start and stop at the origin. So you can take for granted this situation here, and all you need to do now is figure out if we're starting here at theta equals 0, at what value theta do we hit this point? And then you can use symmetry and multiply this area by 2 to get the top half of the loop. So that's the plan that I'm going to lay out. Find the area of the bottom half of the loop. And then multiply it by 2. Because you know it's symmetric, to get the area of the entire loop. Or I should say the entire inner loop. Inner loop. I mean, it says that, but I want to make sure it's super clear. Okay, so your start occurs at theta equals 0. Your goal is to figure out if the start is at theta equals 0, where does the inner loop end? So we are going to find theta right here at 0, 0, which seems silly to you because you're like, wait a second, 0, 0. If the radius is 0, technically this point is 0, 0. So theta must be 0, but at theta equals 0, r is actually -2. I know. So maybe in order to make this really clear, we shouldn't include this as a coordinate point. We should write it as r equals 0. Okay, so we're going to find theta when r equals 0. Now, of course, that's going to happen more than one time, which is where you're going to get this intersection. So the first place that occurs is going to be as we head underneath this inner loop on the underside of it and head through. And the second place where that occurs is down through here when it goes through again. So we don't want the second place where it occurs, otherwise we're getting all this area in between, which we don't want. So we're going to look for the first place where that occurs. So I'm going to set r equals 0, and I'm going to take my equation r, which is 2 minus 4 cosine theta, and set it equal to 0. I'm going to look for the first place where this happens. And by the way, it should be obvious once we find the angle that it makes sense according to our graph. And so we're going to look at the radial line. You can add 4 cosine theta to both sides, divide both sides by 2, and you'll get cosine theta equals a half. So we know that this is going to occur first for theta equals pi over 3. We of course know that this also occurs at 5 pi over 3, but you've made it, by 5 pi over 3, you've made it all the way down here. And that's the second time around. This theta right here, what this represents, when you swoop up through here, is this radial line. Pi over 3. That is where you're getting this occurring. So again, I know it's sort of coincidental with what we did in the last example, but I guess pi over 3 is a pretty standard trig function value. We're starting at 0. We're going through to pi over 3, and that's going to get us this first place where r equals 0. Don't worry about the top half of the loop. Make things easy on yourself and just use symmetry and take your area of the bottom half of the inner loop and multiply it by 2. Before I set this up, are there any questions on what we have discussed so far?
And we can check that in the graph if we put pi equals pi over 3 and it shows r equals 0.
Yes, I'm glad that you mentioned that because I forgot that we did that in the last example. But yes, absolutely, you can check it by going from 0 to pi over 3. I'm going to again zoom standard this time. Every time I do that, it erases what I put in. Okay, so don't freak out if that happens. But from 0 to pi over 3, you do get just the underside of that inner loop. I have a feeling some of you guys are like, wow, this is kind of fun. Maybe.
It
I
is.
really like this. Yeah, I know it's different and it can be challenging at times, but it's cool how you can sort of use what you know about calc and trig in conjunction with what you're seeing in your graphing calculator. It's just nice to be able to put everything together. Okay, so remember I said we were using symmetry. So I'm going to take twice our area. So this 2 comes from the symmetry. And the 1/2 comes from our area formula. So we're going from 0 to pi over 3. We're taking 2 minus 4 cosine theta, quantity squared, d theta. So now remember that this is just the area of the bottom half of the inner loop. And we're multiplying it by 2 to get the area of the whole inner loop. So now it just comes down to algebra, trig, calc. Everything gets combined here. I love that. I love to use all of the things. So we're going from 0 to pi over 3. Let's see. 2 times 2 is 4. 2 times -4 is -8. Minus 8 is 16. And then plus 16 cos squared theta d theta. And then remember that cosine squared u is 1/2 times 1 plus cos 2u. So we're just going to go ahead and use a power reducing formula to reduce this down. So 16 times 1/2 is 8, and then we'll have 1 plus the cosine of 2 theta. And then simplify. 4 plus 8 is 12. Minus 16 cos theta plus 8 cosine 2 theta d theta. Oh, yikes, I'm ready to integrate. Here I am writing my integration symbol over again.
Quick question, where did we get the 12 from?
So the 12 came from the 4 and the 8.
Oh, okay.
That's fine. Yeah, and then this just came from distributing the 8. Okay. The derivative of sine is cosine, so we'll have minus 16 sine theta, and then plus 4 sine 2 theta, and we'll take that from 0 to pi over 3. If you want to factor out a 4, you can. I don't really think it'll make much difference. Up to you. And then you just have to know your trig function values. Your sine is going to be positive in both pi in quadrant 1 and quadrant 2, pi over 3 and 2 pi over 3. Sine of 0 is 0. You don't need to worry about any of those terms. They're all going to 0 out. 12 over 3 is 4. So you have 4 pi. Sine of pi over 3 is root 3 over 2. And same with sine 2 pi over 3. Same reference angle, sine's positive in quadrant 2. So you'll have minus 8 root 3 and then plus 2 root 3 gets you 4 pi minus 6 root 3. So some of your answers are going to be a little bit irrational, very irrational, but that's okay. Make sure you leave them exact. Don't give me decimal approximation. Make sure it's exact. I have 2 more examples to do, and I'm only going to have time to get through one of them. The last one I was going to do had like 2 parts to it anyway. I was going to look at it 2 different ways and do 2 different things to it. So technically it's more like 3 different examples. So I'm going to do this one with you now, and then the last one I will do asynchronously for you soon, very soon, because I want you to have it so that you're ready to head forward into next week. And really, we got through more than I expected to tonight, so that's good. Oh, I'm on paper again. Here we go. That was the inner loop. I guess it's because we didn't take the quiz. We had a lot of extra time. Kind of nice. All right, so the last one that I'm going to do with you right now is example 4. I think it's 4. 3. Okay, 4. Find the area of the region. Outside r equals 1/2, and inside r equals cosine theta. And it is really helpful if you graph these also on paper. I know seeing them in your calculator is also really helpful, but for me, I like to just be able to look at it and kind of shade things, and I like to have it right in front of me on paper. Everyone's different. Now, r equals 1/2. If you remember your r equals, that's just a circle centered at 0, 0 with a radius of 1/2. So you can go ahead and plot that now if you'd like, but you can see that we're going to have to zoom in here anyway, just because that's going to be a really small circle. So we have r equals 1/2. And then the other equation is r equals cosine theta. We did some work with that in 9.3, I think, or 9.4, probably 9.4. But it was just your unit circle shifted, or I shouldn't say unit circle, but that was just your standard circle shifted over. Remember, cosine was shifted to the right and sine was shifted up. That's what your graph is going to look like. Go ahead and zoom standard, and you can see it's teeny tiny. So you're not going to find that very useful. Oh, I also saw it went, so let's go ahead and zoom in. You might as well just zoom into the center, because you might need to even zoom in again. Oh, look at that. Interesting. Interesting. I almost want to zoom in one more time. It's going to be too much just to watch that again. 1, 1, 2. Crazy, right? This one, r equals 1/2, graphed itself in just one revolution from 0 to pi. The other one took 2 pi. Crazy. I'm going to zoom out again a little bit. All right, so there's your radius of 1/2, and there's your cosine graph. So you take that to 1 in each direction. The radius of 1/2 is going to be right about here. Label these. Do the best job you can if you're graphing them. It can be helpful to you. Your other graph, maybe it's kind of hard to see, but this is 1 unit right here. It's just spanning this 1 unit from 0 to 1. And it's going up also to 1/2 because it's got the same radius. It's just shifted over. I know I'm doing a terrible job. I can't graph circles. Sorry. I know. I've just given up. There are some years I'm better at it than others. This is the best we're going to do right now. So find the area of the region outside r equals a half and inside r equals cosine theta. Okay, so outside a half, inside r equals cosine theta. So just be careful here with just the wording, even making sure that you're choosing the correct region. If you're inside cosine theta and you're outside a half, that means that the only place you can be is in the part of cosine theta that's not inside r equals a half. So your region looks like this. Now, what you're going to do here, and I know normally when we graph, we're so focused on making sure everything is accurate as far as where our points lie. In this case, it's not really going to matter. All we need to do is really figure out where these intersect. I want to know what theta has to be in order for these two graphs to intersect. And then I can do a couple of different things. One of the things that I can do is use symmetry and just find the area of this top half that's above the x-axis and then just multiply it by 2 to get the whole thing. Otherwise, I'm going to have to find the negative angle that's down here in quadrant 4 and then go up to the positive one. I think we're probably going to go with symmetry if I know us, which I do, if I know me even. We're going to focus on finding the area of r equals cosine theta and taking off the area that's on the inside. So I don't want that. It's no good. I just want this area that's shaded minus the area that's inside of it. So that's the plan. So we are going to find the area, let's say above the x-axis that is inside r equals cosine theta and subtract off the area inside r equals a half. Because when I take this, sorry, I know you're writing, and here I am trying to do my little pencil thing over it. As I'm looking at theta equals 0, I'm talking about what's happening right here. And as I increase that angle theta up, and eventually I work my way up to this radial line that is the intersection point, I'm looking for this theta. As I work my way up, I had a point and now I was so focused on not covering up what you were writing and I lost my point. So we're working our way up through theta. I don't know. As long as we make it all the way to this intersection point, what we're really including here is the area of this whole piece. So we need to focus on taking off that bottom part. So if you're thinking about sort of your radius, how it heads out here, we need to subtract off the piece that is inside there. So that's the plan. In order to do that, I need their intersection points. So we talked about how to find the intersection of two polar graphs earlier. We just set them equal to each other. So we'll do that now. And once again, we're looking at the exact same equation we've seen all day. It's a weird coincidence. If this doesn't come up at all on your homework, I won't be surprised. Cosine theta equals a half. Hopefully, we've talked about it so much that everyone is very aware that the cosine of pi over 3 is a half. So this happens at pi over 3, and it should look like that to you when you look at the radial line. So when I set this integral up, I'm going to set it up as one integral. I'm going to take the area of this whole portion all the way up to cosine theta, and then I'm going to subtract off the area of the inner portion, which is r equals a half. Before I set up my integral, are there any questions on the figure? And this might be one you have to stare at a little bit. The one I'm going to do asynchronously is kind of like this as well. So you'll see another one like of this type. And by the way, the one I'm going to do asynchronously, I'm going to move the region around that we shade. So it'll be like, okay, maybe now let's find the area over here versus over there, and or maybe even the intersection. Maybe I'll add another part to it. I think that's what I'll do. I'll add another part. Because really the setup is what I want you to really get down here. It's not the integration itself, it's the setup. All right, so I'm going to go from 0 to pi over 3. I'm going to use some symmetry so that I can take that off. I think if you want to wait until the end to use the symmetry, if you feel like that's going to be confusing to put that out there, that's fine. I'm just going to use it now, otherwise I might forget that it's even there at all. Okay, so the 2 is for the symmetry. The 1/2 is part of your area formula. We're going from 0 to pi over 3. I'm taking the area of the outside function. That whole thing is included when I find the area. It's going to give me all of that. And then I'm going to take away the parts that I don't want. The parts that I don't want are the parts that are inside r equals 1/2. So these are just going to be the trickier ones just because of the setup. So this will be the whole thing. The whole region from 0 to pi over 3, and this will be the inner portion. This area right here gives you the area above the x-axis that's shaded. Multiply it by 2 and we'll get the whole shebang. Again, this might be something you have to stare at later, but are there any questions here right now? Wonderful. And you've already been integrating stuff like this all day today. So this will be cosine squared theta minus 1/4 d theta. And we're going to go ahead and switch this out using our formula. So this will be 1/2 times the cosine of 2 theta. 1 plus 1 or 1 plus, who cares? Doesn't matter. D theta. And then we'll simplify. Now, when I simplify, I'm going to be distributing this 1/2 into the parentheses. So we'll have 1/2 minus 1/4 leaves us still with positive 1/4. And then we'll integrate. So we'll have 1/4 sine 2 theta plus 1/4 theta. And we'll go from 0 to pi over 3. So we'll have 1/4 sine 2 pi over 3 plus 1/4 times pi over 3 minus 1/4 sine 0 minus 1/4 times 0. So these two are both going to 0. The sine of 2 pi over 3 is positive root 3 over 2. I am totally fine with you leaving this as 2 terms. You don't need to worry about combining radicals and pi's into 1 term. this is fine. Okay, that's all I have time for tonight. I'm going to do the last example asynchronously. Like I said, I'm going to do parts A, B, and C for it so that you get to see different setups depending on which region we're focusing on, because I really want you to feel like you're getting a handle on how to set up these areas. So I'm going to do that. It might be tomorrow morning before I get to it, because it might be a little too late for me to do tonight. I got to put my kids to bed. But I will do that and release it to you soon, definitely by Friday morning at the latest. If you have questions, I will be in the office hour for another 20 minutes, so do stick around. And otherwise, I'll put up some homework problems from 9-5, and then I'll get you started on 9-6. Everything will be due Wednesday because your test is Wednesday. So that is all. Have a wonderful evening.
You too.
Thank you.